Hello, last time we visualized how to solve a problem in 2 dimensions. So we essentially had one objective function, we had multiple constraints, we saw the feasible region, and we saw how, if we were to map the objective function, how we can get to an optimal solution. Now, I want to take this one step further and show you that there are cases where a problem could be infeasible, unbounded, it could be multiple optimal, an infinite number of optimal. And I've basically drawn on the blackboard here different scenarios. So let's have a look. The very first scenario here is what I essentially showed you last time. We have a feasible region that is bounded. Okay. In yellow you have the constraints that have been drawn here. Again, remember this is in 2 dimensions, x1, x2 are the two variables. And we have an objective functions that when we decide to map it, right, as I'm going up it actually increases, and then I reach a single optimum at the end. Okay. So in this case this is a unique finite optimal, but the feasible region is bounded. Okay. That is quite typical. Okay. Now let's look at the second problem. Okay. The second problem is the following. I have mapped the constraints as well, but the feasible region is unbounded, right? So because all of this, and if I go further and further, that is still part of the feasible region. However, when I map the objective function, okay, this is where I'm going, okay, and I have a unique finite optimal solution. Okay, let's look at this other problem here. Here. And this would happen a lot in, say, simulation or more theoretical cases. Generally in geography and spatial optimization, this does not really happen too often because generally the population that we are trying to cover is not homogeneous. In this case, I have mapped the constraints. Okay, the feasible region is bounded, but when I map the objective function, right, I realize that I have a finite number of optimal that are along this line. Now, I say finite because typically we are dealing with integer problems. Okay, if this was a where we didn't have integer constraint, you could have an infinite number of optimal solution along this line. Let's look at another problem. Okay, where here we have the same problem as before. We have an infinite number of optimal, right, or final number of optimal if you have an integer problems right here, okay, but then the problem is unbounded, right? So in fact, all of this part is also feasible region. Let's look at this other example where you have a problem, and this may happen every now and then. You have a problem when you map the constraint here, and then you have an objective function value here that is can keep on increasing. So for instance, you could have trying to maximize coverage, you have an infinite number of places where you can put cell towers, you have an infinite amount of budget, right? So you can put them everywhere and so on and so forth, right? So this could be unbounded. Last example, and that one is also quite common, right? You map the different constraints, right? But if you look at the constraints, you need, the feasible region is outside. The feasible region is outside here, feasible outside. So there is not any feasible region, and so the problem is infeasible. This will happen every now and then. For instance, you may have constraints that are way too tight, that are just not possible. For instance, right, you want to open, let's say, 3 new schools, but your budget makes it impossible. So that's where you may have to revise some constraint to make actually the problem feasible. Okay, so keep this in mind. This is quite relevant, especially when you use, let's say, Cplex, and Cplex tell you, okay, this is impossible, this is unbounded. No, you can go back and see how this relates in 2 dimensions.